So, hello everybody, welcome back. In the next hours or so, we are going to work with climate station data. So this morning we worked with river discharge and or river height or temperature data. And now I would like to move to a different variable, and that is the properties of the atmosphere. So we are first going to look at measurements that we can do with custom-made sensors for the atmosphere. So this is an example of a station that we put up last year. This is at the bottom of the Trijuli River at roughly 489 meters. And what you see here is a GNSS antenna. We are going to talk about this in 1 or 2 hours. And for now, we are going to talk about this device here, which is just an enclosure of a temperature, relative humidity, and pressure sensor. So Taylor was showing you this morning the different sensors, and I just wanted to point out the sensors that are inside there. So you have essentially the controlling unit, which is that Android, the feather, that is just reading the data. This is a very tiny little piece, the same piece that we passed around before. And this tiny piece here is the relative humidity and pressure sensor. This is a very nice one. It allows to measure pressure differences that are the equivalent of moving up and down by 1 meter. So those devices are also used within drones to measure the height of a drone, for example. So these are very, very sensitive devices, and they are about 10 euros. If you spend 20 euros, you can get a super sensitive device which can measure 0.5 meter pressure difference. I don't know if you need that, definitely not for atmospheric monitoring, but if you are using those devices for measuring the height of a drone, then it's a useful thing. So we have pressure, and then we have a very little temperature sensor that comes already pre-packed. We just ordered it this way because it's easier and cheaper. So this is our temperature sensor, and whenever you see such a device, the same device as this device is essentially just shielding the temperature sensor from direct sunlight. You don't want to have this temperature sensor in direct sunlight because then you're measuring the solar temperature. You want to have the ambient temperature. So you have that little device on top. Is like a little enclosure that just shields it from the sun, and then the measurement sensor is right here. So it's a tiny little device, which is, very, very precise, and it's very easy to hook up. So what we have here is a station. I'm going to zoom in a little more. What we have here is a station that combines relative humidity, temperature, and pressure with GNSS measurements, with GPS measurements that we are going to talk about in a little bit. So this is an example of such a station, and we are going to look at these data in a few seconds. I just wanted to point out the usefulness of those temperature measurements. Taylor was walking you through a pandas data frame, looking at temperature changes. Setting up those stations is extremely useful for understanding the energy fluxes in the environment. Meaning energy fluxes means in what direction is the wind blowing, do you have sudden temperature drops, sudden temperature increases. Specifically setting up a few of them gives you the gradient. So the difference between them, for example, at different heights. We talked about the lapse rate a little bit ago. So for those topics, having set up a local station is very, very important, because you almost cannot do that with remote sensing data. You can measure temperature very, very accurately with remote sensing data, but you don't get 24 measurements per day. So if you are interested in the diurnal cycle, the differences between day and night, you will need to set up your local station. So if you spend 50 to 100 euro, you can set up your own station. You can also buy one for a couple of €1,000, but this is likely outside the budget. This is also outside of our budget, right? So this is why we are constructing those sensors ourselves. The quality is the same. It's just that the packaging is a little different. But the sensors itself are exactly the same. So that's the important part. Okay. Have you worked with atmospheric data before? Have you had any experience with relative humidity, temperature, time series? Are you familiar with those data sets? I mean, there exist stations in Kathmandu, for example, right? That measure the temperature. The data set that is available for Nepal, there are several stations by the meteorological department set up around Nepal, but they usually only record 3 values: a minimum, a maximum, and a mean value per day, not the entire daily cycle. And so that's something that we want to look at with these data. Okay, let's move to our favorite computing environment, which is our Jupyter Lab or Jupyter Notebook. And if you look on the workshop webpage, okay, is this still recording? Yeah. Oh, I couldn't. I think because I started that. Just do the desktop. Can you go to display? It just stayed like it after the PowerPoint, right? So, yeah. Okay. So what I ask you to do is, the task is that we are going to look at 2 time series. One is from the lower end of the Trijoule and one is from the upper end of the Trijoule. So if you go on the GitLab or GitHub webpage, in exercises there is a directory that is called GNSS, VWD, and IWV. So VWD stands for Venice wet delay, and this is integrated water vapor. This is something that we are going to talk about in a little bit. If you click on this and look into this directory, you see that there are a bunch of files, and right now we are going to use just 3 files. The NPA1 5-minute climate data, NPA3 5-minute climate data, and the Jupyter Notebook plot climate data. So this is where we are going to walk through and look at what we can do by looking at those climate data that were collected by the stations in the field. So I'm going to start my Jupyter Notebook. And I'm going to go to the GNSS data, and I'm going to say plot climate data. So at some point you should see the Jupyter Notebook read and plot climate data from custom sensors, and this is something that we are going to do together now. So I'm going to wait a second until all of you have opened this, opened that web page or that Jupyter Notebook. Are you able to find it and open it? Yeah? So again, it's called Plot Climate Data. And for now, you only need the file npa1 5-minute climate data. npa1 _ 5-minute _ climate _ data. And that you put in the same directory where you have the Jupyter Lab, okay, or the Jupyter Notebook. Is everybody there? Wait another second till you have opened this. And we are not using any fancy packages here. We are mostly relying on pandas for reading in the data. So pandas is an extremely powerful tool if you are dealing with time series data, specifically in any tabular form. It's also very nice for input and output of files. So whenever you have a file format that is a little awkward and that is difficult to read, or where Excel has issues, pandas is a very nice way of getting those data into a computing environment. And then I'm just bringing in a couple of matplotlib things that allow us to create plots. So I'm just going to show you a couple of ways how you can visualize and plot these data. And I'm also show you how you can change the time zone, because all of these data are being collected in GMT time, that's London time. That's not very helpful for us, here in Nepal, when the sun rises 6 hours later, and the timing is completely off. So you may want to be able to change the time zone, and we are going to talk about this, and this is exactly this dateutil.timezone.tz that can change the time zone on your plots so that you have a local Kathmandu time, for example. And I'm also bringing in NumPy, but I think I'm not even using it. NumPy is, the standard way of doing numerical analysis or modifications. And so again, I can't stress often enough how important pandas is. And there are books written only about pandas. I just need this one line essentially, or 2 lines, to read in the data. I need the file name, and the nice thing about pandas is pandas can automatically read a compressed file. So this is a CSV file. The CSV file can be read by Excel, right? A comma-separated value file. And you can also compress that file with gzip, which is just a standard compressing algorithm that makes the file size much smaller. So you cannot read the file anymore because it's compressed, but pandas can automatically read it and uncompress it. So that's the really nice thing about pandas. It recognizes file extension and can uncompress it readily. So all you need to do is pandas read CSV, and then you give the file name, and then your data is being stored in npa1 _ clim data or climate data. Is everybody has this page open now? So we can walk through there together? Okay. So what I usually do is when I have a data set loaded, the first thing is I want to plot the first 5 lines. And I'm just plotting, I'm using the name of the variable where everything is stored in, and I'm putting a point head. Point head just means you plot the first 5 lines, and if I would do a tail, I'm plotting the last 5. Oops, I need to load them first, of course. And if I'm plotting tail, I'm plotting the last 5 lines. So head and tail is just a nice way of seeing where does your data begin and where does your data end, and getting a general feeling for what this is, right? And what you see here is that we have a couple of columns. We have a date time column. We have the pressure in units hectopascal. That's the unit. We have temperature in units of Celsius, and we have relative humidity. And relative humidity usually goes between 0 and 100, right? It's a relative measurement. It doesn't have a unit. You could use the unit percent, but in that sense, this is not a unit. And for this data, I already calculated a rolling average. We are going to do this together, but I have calculated a one-day rolling average. Taylor was showing this earlier for the temperature data as well, right? The daily average. This is a rolling average, so you essentially take a longer window and you take the average over a longer window. And I'm doing this for all data sets. The relative humidity, the pressure, and the temperature rolling average. So these are the data that are in the CSV file. So one thing you want to be careful of when you import data from a CSV file is sometimes the date vector, the vector or the column that is supposed to contain the time, the date and the time is not being properly recognized. That happens off and on. It depends a little on the format. In this example, it's the case that the date time vector has not been properly recognized, and you can find out by looking at that date time vector. So I'm calling the name of the variable, and I'm calling the column name, and I'm just showing the column name, and at the end of the column name, the data type is object, which means it has not been properly recognized as a date time or as a time vector. That means we can ask pandas to convert it to a date time vector. So all we need to say pandas to date time, and we are giving it the variable name, and we are writing it in the same file back, or in the same column back. And now if we are calling the date time, it is a date time it's a data type date time. So now we have converted it into a format that can be readily understood by Panda. That's the same as in Excel when you choose the column type, right? In Excel you can choose the column types, you can have currency, you can have a date format or something. This is essentially giving us the column type. I just put this step there on purpose to show you that sometimes when you load in a data set, you need to do a little bit of editing to make sure that the data are properly loaded in. The next step we do when we bring in a CSV file, we set the index. So Pandas has the option of creating an index, so essentially sorting everything by a specific column. And because it's a time series, it makes sense to sort everything by the date time format, right? So we are setting an index. We tell Pandas that the data set NPA1 CLIM data has an index called date time, and then the date time essentially allows sorting, automatic sorting by the date time. The format is a standard format, so you have year, month, day, and then time in 24 hours, and this is a 5-minute data set, right? Meaning you have data every 5 minutes. This is fine for our purposes here. So now we are at the point where we can start to do some averaging, and a very typical average that you do is you're taking the mean, the rolling mean. So here we are taking the rolling 24-hour mean, which means that we take an average, or we have a window of 24 hours, and that window of 24 hours we are sliding over the data set. And we are putting that average of 24 hours onto that current point. So this is a very typical thing for smoothing it. 24 hours is pretty long, meaning that you're removing part of the diurnal cycle, of the daily cycle. You could also create an hourly average, for example. If you have very noisy data, you could create an hourly average, which still would maintain the diurnal cycle, right? You still would see the temperature changes. So this is a very typical processing step that you do, where you bring in the relative humidity, the pressure, and the temperature. Again, you could also do monthly averages, right? So you can whatever time you use here, that is the time that you are averaging over. And the dot mean in the end just means that you want to create the average, the mean. You could also do the median or specific percentile if you want to. Okay, and the next tab is a longer plotting that let me just go through here. I want to make sure that that this works. The next is a plotting command, and I just want to explain a few things. Maybe I'll first show you the output plot, what we are creating. So we are creating an output plot that looks like this, with an upper panel and a lower panel, and I'm just realizing that it may be easier if I am showing this as the figure that I'm saving. Oops. Let me just see. No, that's not okay. Let's forget about this. So I'm having an upper plot that starts in May 2023 and goes to pretty much a couple of weeks ago. And on the y-axis is temperature. And those thin dots here are the 5-minute temperature, and this solid blue line is a 24-hour rolling mean, right? You see that this curve is a lot smoother than the 5-minute measurements that go up and down during the day. So Taylor was just talking about the range of temperatures that we have. Here, this is the mean. And you clearly see you have high temperatures with peaks above 30, 35 or near 35 degrees in the summer. And then here in October, things rapidly drop, right? We just have seen that in the other time periods too, right? So we rapidly go from an average of roughly 25, then we go down to an average of 15. And these are data gaps. And I left them in on purpose to show you what this looks like, right? This is where the station lost power for some time in December up until January 1st, and then it lost power again in January. So this is the time slot where it lost power, and here are 2 more time steps where we lost power. So this is what it looks like if you have an incomplete data set because there was a power outage. The bottom panel shows you 2 different data sets. There is a green and a purple curve. The green curve is pressure. So this is just the pressure that wiggles around 950 hectopascal. It increases a little. There may be some kind of a trend in the data. We need to look at this in more detail, but this is the pressure data, and here we have the relative humidity data. So in the relative humidity data, in the beginning of the monsoon was very variable. The scale for this is on the right-hand y-axis, so this goes from 20 to 100%. And then after the monsoons, or during and after the monsoon season, the relative humidity has been continuously high at 100%. That is not really realistic. We know that the air temperature has not been, or the air has not been 100% saturated in the past weeks and months, right? You can feel how dry the air is outside. So this is clearly something where we need to check the sensor. Maybe there is some water that built up there or something else that happened. So this is something that we would need to verify. So seeing this relative humidity time series, I need to look at the data again or look at the station again to make sure that this is not an artifact of a sensor, that the sensor has been kept dirty or something. Anyway, these are the climate data, and I just wanted to talk through the plotting commands that are being done here. So what I'm doing is I'm first creating two plots, a top plot and a bottom plot. So I'm giving it a number of rows. I have a row, an upper row and a lower row, only one column. So meaning that I only have one upper and one lower plot. I'm not having a left and a right plot. And then I'm plotting the temperature and the rolling mean temperature, both in the first upper panel. So the axis 0 indicates the upper plot, and the axis 1 indicates the lower plot. I like to add a grid to it. I set the X label and the Y label. These are the axis labels. It's always important to put those labels on it. And I'm using here the GMT time because it is stored as GMT time in the data set. And then I'm adding the Y-axis as a temperature. Now, if you want to change the time zone, you would do this here. You would set the time zone. For example, if you're using an Indian time zone, then you would put it maybe to Kolkata. If you want to have a Nepali time zone, you would put Kathmandu here. And then you would have the Nepali time zone. So it automatically takes your GMT data and converts it into a Nepali time zone. That makes it easier for plotting. Right now I'm using the GMT time, but you could just change this or uncomment this, and then you would have a different time format. And in the bottom part of this panel, I'm doing the pressure and relative humidity plotting, and I'm just doing one little twist here. Remember the plot? The plot had two y-axes, right? We have a left y-axis showing pressure, and we have a right y-axis showing relative humidity. And I'm doing this by adding a twin axis. So this is this twin x command. So I'm essentially plotting. I'm creating two plots, one for pressure and one for humidity, and they're shown on two different y-axes. So this is one way of creating a plot with two different y-axes. That's a useful thing to know about. Okay, so these were the plots for NPA1, and I'm suggesting in the next 5 or 10 minutes you do exactly the same for NPA3. That is the other data set that is in the GitLab directory, and we are going to do this together. But maybe some of you want to go ahead and do this on your own. So I'm going to create a separate plot NPA3 station data, and you can do this in the same fashion as we have loaded these data, right? So you can load in these data, but instead of loading in the NPA1, I mean, you're loading in NPA3. So this is all you need to do, changing the file name and essentially the variable name to make sure that you have loaded this in, and now you have the NPA3 data loaded in, okay? And what is the next task? The next task is to double check that your date time vector is correct. So we want to convert this. We are using the command from up there, and instead of NPA1, we are doing this with NPA3. And then we can just take the figure command, but we need to change a couple of things. We just have to set everything to NPA3, and then we should have a plot generated. And generating this plot takes a little, because there are several data points to be plotted. And I'm going to wait here for a second till you have completed this. Take your time. So are you able to complete that task? Or so essentially, loading in that CSV file is a typical task that you do when you download a time series, either from other climate station or from some web page. Is often being distributed as a CSV data set, and you can use that as a blueprint to look at this. And while you're working on this, I also wanted to point out that I have a line in here which allows you to save the figure as a PNG file or as a JPEG file if you want to. So if you want to save this figure and use it in a report or put it on a web page or something, you can directly save this as a high quality figure. You just need to use the savefig command, and then you give it a file name, and that saves it as a nice high quality file that you can then use for a report or some other task. So are you able to load it? And if you are able to load it and you do the plot, make sure that you are changing the station name, and also the data frame that you're plotting. If you plot this, you will see that the temperature is a little lower. The temperature on the higher station is roughly on average at 20 degrees during the summer, and then it drops down to just above 5 degrees with a few days of very cold temperature. And this is an example of a very, very nice time series, which is continuous. The station did not lose power, so we have a nice continuous data set here. So this is a very valuable data set for high temperature changes. Yeah, that's thanks to the colleagues that helped setting it up. That's why it's working very well. So, and when you look at the pressure data, the first thing, the green line, look at the green line. The green line it's at a lower pressure, right? Not surprisingly, we are at a higher elevation, right? So you would expect to have a lower pressure. So let's verify the previous figure. The previous figure at roughly 500 meters, we were at a pressure of roughly around 950 hectopascal. If we are at above 1,000 meters, we are at, I think that's 1,700 meters is the station height. We are at roughly 820 hectopascal. So this is the pressure, and you do see some variability here in the pressure, and those are the big storm systems that come in. So you could now zoom in to much more detail here to see what those pressure variations tell us. So what would you do if you want to change the x-axis, right? You can change the scale, the y-axis scale. You could change the scale to make sure that you can pick up those bumps, those lows and ups and downs a little bit better. So all of those pressure ups and downs, this for example, that dip here, that dip that lasted a couple of days is a major low pressure system that migrated through, okay? And that certainly caused significant temperature changes as well, and you see several of those. So those are the monsoonal depressions that have been moving up the valley and impacting this area. So this is nice to see that. You also see that the relative humidity during the monsoon is fairly high, and then it drops down a little in the winter season. I'm just realizing that I need to make sure that I have the data properly. Yeah. So I have not set the index properly. Let me just do this real quick here. If you don't set the index, then the date is off. Give me 1 second. So you may have noticed that the x-axis date was off for a little bit, and that was because I didn't set the index properly. But if I set the index, then we are clearly seeing what the temperature looks like. And this is a station where I got the last data 3 days ago, or the plot includes data from 3 days ago. I mean, we could download now the most recent data, but this is it's a near real-time station. So we get data for this particular station, we get data every 15 minutes. So we do have a very, very high frequency, near real time, as you call it. Okay, so this is, if you're now an atmospheric scientist, you would look into more detail of the pressure changes to see if you can correlate that with big circulation systems that are migrating through, and you would be trying to see if there's something you can say about the strength of a storm, for example. So is everyone comfortable with dealing with the CSV files and loading them in, making those plots? That was the idea of this particular exercise here, that you just get familiar with loading in a climate time series, plotting it, and making some simple analysis with it. Okay. Are there questions or comments regarding the CSV files and the plotting? Good. If this is not the case, then I suggest can we open the door a little to let in some extra oxygen? You know, oxygen never hurts. So there's and in the next 30 minutes or so, I would like to talk a little bit about another component of the atmosphere, and that is water vapor or precipitation. So we talked a lot about temperature, relative humidity, pressure, and other variables that we can measure. The variable that is notoriously difficult to measure is snow and rain, or in that sense, the amount of water vapor that is stored in the atmosphere. And there are different ways of measuring rainfall in the atmosphere. For example, you could have a bucket on the ground that collects the drops, and then you measure the volume or the height of rain that has been collected, and you know the rainfall amount. There are also devices that allow you to measure the numbers of drops that are falling. For example, with a laser, if you have a laser pointing horizontally and it's raining through that laser light, you get a drop size distribution and you get information about how many drops are falling. That's a modern way of measuring the rainfall amount. But all of those methods only measure the actual water, not the water vapor or the potential that is being stored in the air. And as an atmospheric scientist, you're not necessarily interested in how much it rains, but how much moisture, how much total moisture is stored in the atmosphere. And this is what we refer to as water vapor. So if you are interested in understanding big extreme events that cause a cloudburst, when the cloudburst happens, it's too late, right? Then the cloudburst happens and the rain falls, and then the disaster is already happening with the cloudburst. It would be nice to have an understanding before the cloudburst occurs. And this is where water vapor measurements, or as you call it, integrated water vapor, come in. Integrated water vapor is the amount of moisture that is being stored in the air. It's not rain. That can turn into rain, but in that sense, it's only the water vapor that is saturated in the air. And you can measure the water vapor, for example, with balloons that you are letting, if you let a balloon rise through the air, you can get a water vapor profile. Some people also do it with drones, and some people also do it with airplanes. But that gets pretty tedious, and you can only launch that many balloons, and the balloon only gives you the information for one profile where it's exactly going up, right? But those measurements are being done, for example, around thunderstorms to get a feeling for what is the potential. If that thunderstorm is triggering a rainfall, how much rain can we expect? So water vapor is one of the physical variables that is measured to determine the potential of a storm. And the reason why I'm talking so much about water vapor is there's obviously another way of measuring it, right? So this is why we are putting up all of those GNSS sites. And this is what I would like to talk about a little. We can measure water vapor directly in the atmosphere by looking at the delay signal of a GPS or a GNSS. So the old term GPS is the global positioning system that is being used by the American system that was put up by the U.S. Defense Ministry, right? That's the GPS signal. Nowadays you call it GNSS, Global Navigation Satellite Systems, because several countries or nations have their own navigation satellites. There is GLONASS from Russia, There's the European Union with Galileo. There's China with Baidu. There's the Indian system. There's the Japanese system. And then there's, of course, GPS. And the constellation of all of those satellites is referred to as GNSS, Global Navigation Satellite Systems. And this is a very complex topic. We are not going to talk much about the radar data that is being emitted by them, but just think about this is a radar device in space that sends off radio wavelengths on the order of 20 to 30 centimeters. So this is the wavelength of your standard GPS signal. So whenever you're using the Google Map or some other function on your phone, this is using a GNSS satellite system. It uses radio wavelengths roughly with 30 centimeter wavelengths, and it's only using one signal. You call it the L1 signal. So the L1 signal is what all of our phones can receive, and also the signal that what Taylor was talking about earlier today, the reflected signal from a river that gives you the height, for example. But there are many more signals being sent off by the GNSS satellites. They are mostly used for commercial purposes. Like, for example, when you are on a construction site and you're sitting in a truck and you want to navigate that truck at the centimeter scale, then you're using multiple frequencies, or using a differential signal. Or when you have a drone and you would like to control your drone very, very accurately, you're also using additional frequency. So if you have a better antenna or if you have a better sensor, you can record additional frequencies. And those additional frequencies are very, very important for measuring water vapor. And the idea behind it is, now I'm going back to my back to this here. Let's see if this works. Oops, it always starts in this. The idea behind this is, let me show this. The idea behind this is that if you have an atmosphere, or the lower part of an atmosphere, which is called the troposphere, if you have a dry troposphere, the signal goes directly from the satellite to the receiver. The receiver is your antenna. If you have a wet atmosphere, your signal is being delayed, is being refracted, because the speed of light is changing, and you have refraction occurring, so your path through the atmosphere is longer. Therefore, your signal is delayed. And if you have two frequencies, one shorter frequency and one longer frequency, you can measure the difference between those frequencies to measure very, very precisely the amount of water vapor that is in the atmosphere. But you need at least two frequencies. You can use more than two, but you need at least two frequencies. And using two frequencies means you need a better antenna and a better receiver. So this does not work with your standard phones. You need better equipment than this, and we are going to talk about this in a second. So just think about that. Think about it in this way: the more water vapor in your troposphere, the more delayed your signal, the more refracted your signal. You can also envision it this way, that if you have a satellite that is looking very obliquely through the atmosphere, so the path is long, this path gets even longer because the path through the atmosphere is longer, and so it gets refracted even more. So you actually talk about bending. You're bending the ray that is supposed to travel in a straight line to your receiver. This is being bent because of the additional water vapor that exists. And by looking at different directions, for example, a zenith or a nadir point that looks straight down, or a very oblique point, you can essentially make a raster of the atmosphere and can measure the water vapor in the atmosphere. And what we end up doing, we could talk about this for hours, but you just envision that we are taking all those rays that come in oblique, because the sensors are distributed all over in all directions, and we are projecting all of those into the zenith direction. So when we measure the water vapor, we usually measure the zenith delay. That is the delay that is directly above, in a straight up fashion, above your antenna. So this is the delay that we are measuring, and we are creating this signal by taking all of those signals together and just applying a mapping function. That mapping function is in that sense only the sine of this angle. So we're just using very, very simple trigonometry to map all the water vapor in the zenith direction, and this is our delay signal directly above the station. And usually we can think of it as having a radius of, let's say, 20 kilometers, something like this. So when we measure water vapor, think about a cone of 20 kilometers that reaches up in the atmosphere, and we are measuring water vapor within that cone. Now, before I continue and explain this with a couple of examples, I just wanted to point you to the hardware. And the hardware is slightly different than what we have seen before.
So time will suggest that I could maybe have 7 or 8 satellites that it's going to be at the same time. And the one that photo is going to show you now is like 200.
200 or 300.
So it's very different.
Yeah. So.
Mine is also 30 euros versus 30 euros. So you wouldn't be able to do this kind of water vapor separation. You can do that, but it's something like this.
It's more advanced hardware, but also that hardware has gotten much cheaper. That's why we can do this now. It used to be that such a station, a very precise geodetic style GNSS station, was around 20,000 euros. Yeah. So they used to be 20,000. Now, in the last 2 or 3 years, there were new sensors that were developed. The sensors are around 200, 300 euro, so much more affordable. And also the antennas have gotten much cheaper. It used to be that the antennas alone were around 5,000 euro. And now the antennas are much more affordable, but you need a much better antenna. So you can't use that tiny little thing that we've seen earlier today. You have to use an antenna that has this style, and that allows you to record multiple frequencies and also store the data very accurately. These antennas are pre-calibrated, so we know what the delay is from different directions, how that will be treated. So I'm just pointing out that we can use the same Raspberry Pi setup. We have the Raspberry Pi. We have a little sensor that is external, that is connected to a USB port. That is our high precision GNSS sensor. So this is something that allows us to do either geodetic surveys or water vapor surveys. And then we hook up this antenna, and we have built our mounting pole for this. This is a geodetic style mounting pole that then needs to be permanently fixed really tight into or at a site. We can also sometimes we have a plate that we can also put on a roof, for example. Then we put concrete around it, so this should not move anymore. So this is a geodetic style antenna. So this is the hardware that we are using, and the example of such a hardware installed is what I've shown you earlier, this guy here, right? So this is the pole, this is the antenna, the GPS is sitting down here. But this is a setup that is really nice for measuring relative humidity, temperature, and pressure. And here we're measuring water vapor. And the combination of this is a really nice predictor of the potential of big storms coming in. And we see this in the data already. So when we see the water vapor goes up, we know there's a potential for a big storm to arrive. So before we look at the data, I just wanted to give you a few more pieces of information just to give you the context. And what we talk about is we are talking about the zenith total delay. That is the delay of all the rays of all the satellite systems or of all the GNSS satellites that are being received by the antenna, and that there's a total delay. And the total delay is being separated usually between the wet delay and the dry delay. The dry delay just means it's essentially the density of the atmosphere. And that can be described by pressure changes, right? If you go up in the atmosphere, pressure changes, and that also changes the refraction. So that dry delay can be very straightforward, that can be very easily modeled. It's very straightforward. The wet delay is the water vapor, that we're interested in. And usually, the water vapor is the highest in the bottom kilometer. In the bottom 1 or 2 kilometers of the atmosphere, we have the highest wet delay. So that's why when you talk to a person who is monitoring plate tectonics or earthquakes, they always like to set up the station at the ridge crests, because then they have no water vapor or less water vapor. Whereas when you talk to an atmospheric scientist that uses these data to measure water vapor, they always go to the bottom of the valley because they want to have the water vapor. But the bottom of the valley is not always useful for monitoring plate motions because you're not seeing the entire sky, right? You have a limited sky view. But for water vapor monitoring, it's perfect to set it up in the bottom of the valley. And I'm not going into much detail, but I'm telling you that in order to convert our delay signal into a temperature data, in order to create our wet delay signal and convert it into an integrated water vapor signal, all we need is the temperature. There is a very robust relation between the water vapor and the wet delay that we measure, and this is basically a function of temperature. So the higher the temperature, the more water vapor you can store, so this modifies it slightly. I'm not going into detail here. This is a relation that has been first developed in the 90s, that has been revised a couple of times. The more station became available, but essentially, if we can measure the surface temperature, we can convert our delay signal from a GNSS station into water vapor. So in other words, we have our local climate station that measures temperature. We use that temperature and convert the GNSS signal into water vapor. And that is a potential of big storms. So this will be our task. This will be our task that we do in a couple of minutes. And I just wanted to introduce the two stations first. So we are going to use the surface temperature from our climate station data, and we are going to use the wet delay signal and convert it into water vapor. It's a simple pandas operation that we are going through, but we are essentially bringing together two different data sets. One is the wet delay data set, and the other is a water vapor data set. So I just wanted to briefly introduce those stations. You already have seen the station 1. That is a photo of the station. This is what it looks like. We set it up right next to a hydro power station. And what you see here is a sky view. This is a sky view of how well we can see around the atmosphere, so or around the horizon. So this pink line is essentially the outline of satellites that we see, and we see that in the north direction there is some kind of a mountain. We can only see up to 45 degrees height, and everything else is covered, right? You see that mountain that is behind there, so we cannot see the sky there. But in all other direction, it looks pretty good. So this is a really nice station. This is a station up at 1,700 meters. This is not 489. This is 1,700 meters. We put this up in the last year, and this is in a valley where we have more, where it's a little more confined, so we can see the full atmosphere, but it's still a good spot. So we put it up on this roof here. And just to remind you what the data looks like, we are going to use as a temperature data set our temperature data set that we just derived, right? We just looked at this, and this is our second data set from NPA3. We also just looked at this. Now, I think, let me see, what time is it? Should we take a short break? I think we should. Yeah, let's take a short break, and then I'm going to start with the next point. Yeah, you just see. You know what? I'm just going to use the. So, hello everyone, welcome back. In the next half hour, I just wanted to talk about the conversion of the wet delay to the integrated water vapor system, and I wanted to walk you through some of the steps necessary in order to do that. The processing of the GNSS signal, or of the GNSS signals, can get very involved, meaning it can get pretty complex, and it's always a good idea to outsource things. You know, when things get complicated, you start to outsource things, and luckily we can take advantage of many available web services that do the processing for us. So it's often easier to upload the collected data with our sensor to a service that allows the processing. And one of the services that is very, very good and very professional is maintained by the government of Canada. It's a precise point positioning service, so that is used also to derive very, very accurate positions of a GNSS sensor. And this precise point positioning service also allows you to calculate the zenith wet delay. So you just upload the Rhinex file, the file that has been collected by your sensor, and you, a couple of minutes, or usually 30 seconds to 60 seconds later, you get a file with the information about the wet delay. So the submission is very, very straightforward. You can upload up to 5 days of consecutive data. So if you have one file that covers 5 days, you can upload this. The calculation is very, very rapid. And the reason why you would want to use an online service is that the online service always makes sure that you have the newest clock files, the newest orbits, and all new metadata information for each of the satellites, so that you don't need to do this locally. So they take care of this. So that interface is fairly straightforward. You can just choose a file, upload it. I mean, you have to make a free account first, but then you upload it as a file. and 60 seconds later you get a zip archive, and the zip archive contains several pieces of information. For example, it also contains a summary report. And I just want to point out the summary report. This is for the station NPA-1 at the very bottom of the Trishuli River. This goes from September 2nd to September 7th. That's the start day and the end day. So we have 4 days and 39 hours and 59 minutes, so essentially 5 days. I just wanted to show you what the accuracy of this station is. So we get the very, very precise position of this location, and we have the precision essentially down to the millimeter. Because we have observed up to for 5 days, many different satellites and many different satellite systems we are using. So we have a very, very precise position. And if we have a precise position and the station is not moving, we can use the delay signal to get our water vapor content. And this is exactly something that we are going to do now. So we are not going to do the processing. I'm just explaining you again. You upload the output file from your station. You can look at the PDF that you get in return, and we get a file that is called .tro for troposphere. Troposphere is the lower part of the atmosphere, and we are going to work with this file in Pandas. So we are going to load this in as a CSV file, and we are going to convert our zenith wet delay into integrated water vapor in millimeters, which can be used as a storm prediction. I just wanted to point out that we are using an online system, and the online system is very useful. If you do this continuously, if you set up your own station and you run this continuously, maybe even daily, you want to set up your own processing system locally, because you don't want to upload the file every day. And there is software available that does this. This is open source software. One example is the GNSS software defined receiver, SDR. That's a little pun. Usually it's SDR stands for software defined radio. It's a software that allows you to do a lot of processing, even complex tasks with Rhinex data locally. That's one of the examples that could be used. Another example is the precipitable water vapor. So this is a software that has been developed specifically for turning wet delay into integrated water vapor. So these were the two packages that I wanted to point out. They allow you to do the processing locally. If you do this only once in a while, then the PPP service from the government of Canada is the way to go. It's much more straightforward and gives you the exact same precise results, but you need to upload the file. Okay, so in the next 20-30 minutes, I would like to walk through one of those examples. So please go to your folder that is called GNSS, Zenith Wet Delay Integrated Water Vapor, and there are a couple of files that you have to get. Please get the two directories, the NPA1 PPP and NPA3 PPP. This is the output from the service from Canada. So I'm just putting the output here. If you're interested, you could also get the Rhinex files. These are the files written by the receiver, but you don't have to do that. And you already have the climate data. And then the file that we are going to work with is called plot GNSS _ tropo, or tro for troposphere. So this file, plot GNSS tro, is a file that describes how you can turn the wet delay signal into a integrated water vapor signal. And I'm going to open this, and I ask you to do the same. So please get the two directories, NPA1 PPP and NPA3 PPP, and this Jupyter Notebook, and put it all in the same directory where you have the climate data that you worked with before. Yeah, and then just open up this Jupyter Notebook, and we are going through this together. But I just wanted to make sure that we are all. I'm also putting the link here. I'm putting here the link from the Canadian government servers for the PPP output, and I'm also linking a couple of papers. If you're interested in reading up on this, you can use those links. These are the links to the papers that describe some of the theory behind it that we are not covering here. So is everyone able to open this up? Yeah, and then we can start working through here. So again, please make sure that you get the data. So again, we are downloading, or we are first getting our climate data. Remember, we have to use the temperature in order to turn the wet delay into integrated water vapor. So we are getting our temperature data first. This is what we did an hour ago. We're doing all the conversion steps. And then we are going to load the file that is called NPA1, then the station name. The file name also contains the date. This is 2023, and then the 245th day, that is the 2nd of September. So in the GNSS world, you count the day of the year, DOY. So you count the day of the year, and then, so we start on the 245th day of the year plus 5 days. So this is our input data, and this is the .tro file. And here's a little reader that I put together for reading these files. So we are just reading this file. This takes a second, and once we have read it, we have our dry delay, wet delay, the standard deviation wet delay, and the standard deviation of the total delay. Is everybody with me so far? Are you able to load this? I'm going to wait for a second, just making sure that we are all at the same speed here. So I'm looking here at the first 5 rows and then the last 5 rows. And if you are interested in getting the day of the year, Pandas has the option of getting the day of the year from your index. So that would allow you to turn the 245 and the file name into a date if you want to. Or if you have a longer time series, let's say you have a year time series, you could separate it out by days. So in the GNSS world, you often think about days, and the days are always referenced to GMT time. It's always a London time. Yeah, so it's just the convention. So now what we want to do, we want to, our time series, our climate time series is much longer, right? Our climate time series goes from May to last week. But our GNSS time series only goes from the 2nd of September to the end of the 6th of September. So I'm creating a little index here to just clip out relevant times from the time series. So I'm getting the start date, the end date, and then Pandas has this very nice way of creating a mask. Essentially, the time after the 2nd of September and the time before the 7th of September, they are being created as a mask. And with the mask, is a binary mask, we can just extract exactly the temperature relative humidity data for that same time frame of the GNSS data. It's a very simple slicing operation. I just wanted to show that you can do that fairly nicely. It's very often your time series don't match, right? One is longer than the other ones, and you want to make sure that they match. So you're just clipping them to the same range. And then we can use the plotting function that we had before. So we use our troposphere, our wet troposphere, and we are plotting the delay signal for our NPA1 signal. So this is just the wet delay. This is not the water vapor yet. We have not converted it into water amount. This is the pure GNSS delay. And what you see here is that there's a diurnal signal. I'm going to scroll a little up. So down here we have the temperature data. We are starting September 1st. This is September 2nd. And this is here September 7th. This is our temperature data. Noon, midnight or night, noon, early morning, noon. And then this wet delay data is above here. And you always see that the highest water vapor amount we have in the afternoon, at least for those couple of days. And then here we have a day that is very, very dry. But usually you have those late afternoon high water vapor amounts. And those of you who work and live in the mountains know that's the time when we have the most humidity, and we see that very, very nicely. So we see that in some days you have a little longer period, in some other days it's only a peak period, and in other days we have much lower water content. And we always see that during the night it's the lowest, also because the temperature is going down, right? You decrease the amount of moisture that you can store. We could plot them both on one graph, or if you have a better lineup in the monitor, you can see those temperature data. So again, we can use this temperature data with the equation that I was pointing out before to convert our wet delay into integrated water vapor. This is done here. This is just a simple application of the globally used equation with constants. So we have constants to convert temperature into millibar, and then the amount of water that can be stored per degree or per Kelvin temperature, and then we have the amount of, or the density of water vapor. These are constants. We put them together, and as a variable we only use our temperature data set. This is then multiplied with our then it's wet delay, and this conversion factor, usually around 1.5, and it varies between 1.4 and 1.7 usually, is the conversion factor that converts our wet delay into integrated water vapor. So I'm doing this, so I'm clipping my data that I did before, and our tropospheric wet delay data is 30 seconds that I uploaded, and our climate data is 5 minutes. And Taylor was earlier talking about that the high frequency data, sometimes it's a little overkill to do things in one step size. We know that the water vapor would not change within a couple of minutes. If we have a storm coming, the storm usually needs at least 20, 30 minutes to reach us. So it's fine if we use 5-minute data. So I'm resampling the data to 5 minutes, and we are just extracting the water vapor every 5 minutes. We could do it every 30 seconds, but that would be overkill. We don't expect the water vapor to change that rapidly. So I'm resampling the water data to 5 minutes, and then then I'm merging those two data sets. So I'm having my troposphere data set and my climate time series, and I can merge them. I can tell them that we should merge them by the index, and the index happens to be the time. Since both data sets have GMT as an index, we can very readily merge them, and we can then have one table that contains our information from the GNSS data and the conversion factor. I'm just bringing in the conversion factor. I'm not bringing in the temperature, because in the end we only need the conversion factor. I mean, the alternative would have been that we resample our climate data to 1 minute or something. But again, we don't expect temperature to change at the 1 minute level. So I think it's fine if we work with 5 minutes. And then we can put it together as one plot. Oops, station name, I need to it in there. I'm sorry, I forgot this. Maybe I had it in an earlier one. Station name is equals NPA1. So this now is our integrated water vapor, and we have now units of millimeters, meaning the way you interpret this is that here we have water vapor above us, 55 millimeters is the water column above us, the troposphere, usually the lowest kilometer. Meaning, if it would rain, we would have 55 millimeters of rain coming down, which is quite a bit. So, you know, an hourly rain rate of everything above 20 millimeters is pretty high. 50 millimeters is a decent monsoon storm. That gets really wet then. So this tells you the potential that this atmosphere or this specific atmosphere has for a big storm. So this is now in September. I don't expect there to be a lot of water vapor in the atmosphere. If we do it in August, it would be different, right? There would be more water vapor. So this is where an analysis could come in, where you look at the peaks of the water vapor to better understand how much potential a day has for storms. And when we set up those stations, we set them up along the valley because we wanted to see how the storms propagate into the valley. So we have the lowest station at 480 meters, the highest station at 1700 meters, and maybe next week we are able to set up one station even higher. Let's see what the roads look like. But the idea is to better understand how those monsoon storms propagate up the valley and where we have the peak water vapor amount. So this is you could use this directly and do a hazard analysis to identify this is a dangerous scenario, this is a less dangerous scenario. So that's it goes in the direction of the predictive capabilities.
This will also tell you how many storms and their losses. 500,000 or 500,000.
And this is what we want to do in the next couple of minutes. We are going to bring in the NPA3 station. That is the highest station at 1700 meters. And we are comparing both water vapor contents. Just for a reference, we expect that there is less water vapor at higher elevations, right? Because the atmosphere is cooler, it's higher, you can store less moisture. So we expect that there is less water vapor. So we can just go through these a little quicker. So we are going to get our Let me just make sure that I have the right files. I'm getting my NPA 3 station data that is up at 1700 meters. I do the resampling, the conversion, and I can then create a plot that compares both stations. So the yellow one is the water vapor at the high elevations, and the blue one is the water vapor that we just generated. And you see it is almost twice as high, but you also see that the relative change is different. And that's where you now would need to do a time series analysis to identify how the propagation of storms changes through time, for example. That will be a separate analysis that we are not looking into here, but you would clearly see where you have a big event and a less and a lower event. So, you know, the clear diurnal cycle that you have high water vapor in the atmosphere in the afternoon and low water vapor in the early morning, that diurnal cycle is also true for the high elevation, but it has a lower magnitude, right? You only go from 40 to 30 millimeters of water vapor. In the lower elevation, you go maybe from 60 to 40. So you have a different amplitude of daily range. So there is much more moisture recycling going on at the lower elevation. Okay, is there anything that we should discuss? Are there questions regarding the water vapor analysis? You know, that's something that if you are interested in installing such a station or do it with your university, you know, that's a very useful product to have if you're looking at the big storms, you know, understanding what is the amount of water vapor that gets stored in the atmosphere, and then trying to derive predictive capabilities from that.